Welcome to Tomorrow Unveiled. This week, well, the energy world didn't just pivot. It feels like it executed a full, calculated strategic turn, doesn't it?
It really does. Our dedicated research team, the data they've pulled together, it confirms this profound shift happening. It's a move driven maybe less by pure environmental goals and more by immediate industrial necessity.
Yeah, necessity. And we're calling this the green code hot core era.
That's, I think, the most precise way to frame it. The green code. That's all about the surging, frankly, non-negotiable power demands. Think AI training clusters, massive hyperscale data centers.
Right, and advanced manufacturing, too. The thing's really reshaping global commerce.
Exactly, and all that green code stuff requires the hot core, energy that's not just clean, but, and this is key, reliable, high-density, carbon-free, and, available 24/7.
24/7. So we're talking advanced nuclear fission, SMRs, small modular reactors.
Primarily SMRs right now, yes. And increasingly, we're seeing a real acceleration in fusion energy development, too. That's part of the hot core picture.
Okay, so our mission on Tomorrow Unveiled today is to really dig into the source material that shows this shift isn't just theory anymore.
No, it's commercial, it's policy, it's happening, like, right now.
We've got historic commercial deals, pretty dramatic policy changes from major governments, and critical technical breakthroughs, all stacking up, really, in just the last week or so.
It's been quite a week, and it confirms this transition is really in motion.
So we're here to unpack what this new focus means strategically for the future energy grid and, well, fundamentally, what it means for you, whether you're an industrial user or just paying the bills at home. Let's jump straight in. The source of this pull, the demand side. When we talk about AI's energy use, I mean, it's not moderate growth, is it?
Oh, not at all. The scale is genuinely staggering. And critically, it's the quality of the power needed. That's non-negotiable.
Quality meaning?
Constant and clean. It's the difference between, say, powering a suburb and powering a massive supercomputer complex. The research team that compiled this info, they emphasize the demand from large AI models, hyperscale clusters. It's not just vast amounts of energy, it's gigawatt-scale continuous power.
Gigawatt-scale. Continuous.
Yeah, these places are designed for nonstop operation. If the power flickers, even for milliseconds, you're looking at potentially catastrophic data loss, corruption.
Millions of dollars of computing work just gone.
Exactly. Wasted. So relying only on intermittent sources, wind and solar, even with huge battery backups.
It just doesn't pencil out economically at that scale.
It becomes incredibly impractical. You'd need, unprecedented amounts of storage, and you'd have to overbuild the renewable capacity massively just to guarantee that, say, 99.999% uptime.
And the infrastructure for that kind of backup.
It simply doesn't exist today, not at that scale. And it's certainly not cost-effective compared to high-density, dispatchable power. This absolute need for reliability, that's the shockwave hitting the energy sector.
Okay, and that shockwave, it brings us right to maybe the biggest commercial deal we saw. This historic agreement between the Tennessee Valley Authority, TVA, and Entra One Energy, NuScale Power's partner.
Yes, the TVA Entra One NuScale deal. 6 gigawatts of SMR capacity.
6 gigawatts. Let's really try to grasp the magnitude of that.
It's more than just a big deal. It's genuinely a seismic shift. 6 gigawatts, that's 6,000 megawatts, of small modular reactor capacity, planned across 6 different plants within TVA's territory.
6 plants.
And to put that in perspective, this single program is the largest SMR deployment initiative in U.S. history, period. It absolutely dwarfs previous proposals. It signals the industry is moving beyond single pilot projects
Towards actual fleet deployment.
Fleet deployment, mass production thinking.
And what's critical here is that this power isn't just vaguely aimed at, like, the energy transition. It has a very specific target customer in mind, right?
Precisely. It's the direct answer to that green code demand we talked about. The research data explicitly states this capacity is required to power the equivalent of, wait for it, 60 new hyperscale data centers.
60. Or what was the home equivalent?
About 4.5 million homes. But the data center number is telling. This isn't theoretical future planning. This is a major utility answering the call from its largest industrial customers.
Who are saying, we need stable, clean 247 power, and we need it now.
Exactly. And that completely inverted the traditional risk calculation for nuclear. For decades, the risk was building it, the high cost, the long timelines.
That's infamous cost overruns.
Yeah. But now, the risk of not building that reliable capacity and potentially losing huge industrial investments to another region that can supply the power, that risk is seen as far greater.
Okay, speaking of risk, Those historical projects like Vartel or VC Summer, they ran into huge financial trouble, partly because the utility had to absorb all that balance sheet risk.
Yeah.
How does this TVA deal tackle that old problem?
This is the really clever part. The financial innovation. It fundamentally shifts the structure using a public-private partnership.
Okay.
Entro Energy, the private developer, they're the ones who will actually finance, own, and operate these 6 SMR plants.
So the capital burden isn't on TVA directly?
Correct. TVA, as the utility, commits to long-term power purchase agreements, PPAs, for the electricity.
Yeah.
So that massive upfront capital risk, especially for a first-of-a-kind or FOO technology.
Which utilities are typically very wary of.
Exactly. That risk gets transferred from the regulated utility to a specialized private investment entity, one that's structured precisely to handle that kind of development risk. It's a critical, you could say, innovative de-risking step, really designed to speed up SMR commercialization.
So SMRs are moving from maybe a policy wish list item to a standardized industrial product or service.
That's a good way to put it.
But the advanced fission world isn't just SMRs. We also saw big news for Generation IV reactors, specifically from TerraPower. They're tackling the flexibility issue.
That's right. TerraPower's Natrium reactor, Bill Gates' company, they signed an MOU, a Memorandum of Understanding, with Evergy. They're exploring siting a reactor in Kansas.
And Natrium is different from the SMRs TVA is getting.
Yes, it's a different beast. It's a 345 megawatt electrical sodium-cooled fast reactor that's already advanced tech. But the real game changer is its integrated storage system.
Okay, the molten salt storage, let's focus on that. How does that change how nuclear operates? Traditionally, it's just baseload, right? Steady output.
Exactly. Traditional nuclear is inherently baseload. It likes to run flat out because ramping up and down is complex, inefficient, sometimes not even possible quickly. But Natrium, it has this integrated molten salt energy storage system.
So it banks heat.
It banks thermal energy. When electricity demand is low, maybe overnight, it stores excess heat generated by the reactor. Then when peak demand hits, say, late afternoon, everyone gets home, ACs go on, solar power drops off.
Then it uses the stored heat.
It dispatches that stored heat through its steam turbine, boosting power output significantly.
How much extra power are we talking?
Yeah.
And for how long?
The plant can ramp up its output from the standard 345 megawatts to 500 megawatts. And it can sustain that boost for over 5.5 hours.
Wow, that's a pretty significant jump. Over 45% increase.
It's huge. It makes Natrium what we call a firm, flexible asset. It transforms nuclear from being just this flat, inflexible baseload supplier into a dispatchable resource, one that can actively work with variable renewables.
So you pair Natrium with wind and solar.
And the Natrium takes over the heavy lifting precisely when the wind isn't blowing or the sun isn't shining. It's basically nuclear designed for a modern grid that has a lot of renewables.
Okay, so we've got the market pulling hard, that's AI and data centers.
Yeah.
We've got the advanced tech improving SMRs, flexible Gen fuel reactors. But none of this happens, right, if you can't solve the biggest choke point, which the research our team compiled kept highlighting.
The fuel. You absolutely nailed it. It's the fuel supply chain.
That's the critical constraint.
It is, particularly for these advanced reactors. The issue is the supply of high-assay, low-enriched uranium, or HALEU.
HALEU. Okay, refresh us. How is that different from standard reactor fuel?
Standard reactors, the ones we've had for decades, use uranium enriched to about maybe up to 5% of the fissile isotope U-235. Advanced reactors, partly because they often have smaller core designs and want to run much longer between refuelings, they need higher enrichment levels, somewhere between 5% and 20%.
So higher concentration of the good stuff.
Pretty much.
Yeah.
This higher assay HALEU, it allows for greater energy density, better fuel efficiency, and it means the reactor itself can have a smaller physical footprint, which is really important for SMR economics.
And historically, this specialized HALEU, who's been making it?
Well, that's the problem. Russia. For many years, Russia, specifically Tenex, part of Rosatom, was the primary, often the only, significant global supplier with commercial HALEU production capacity.
Right. And relying on Russia for critical fuel, that's obviously a huge strategic vulnerability now.
Enormous. A massive national security and energy policy liability for the West, especially now that these advanced reactor projects are accelerating so quickly.
So the U.S. government saw this coming and reacted. Tell us about the DOE's Fuel Line pilot program.
Yes, the Department of Energy launched this program specifically to build up a secure domestic HEU fabrication infrastructure, get us off that foreign dependency.
And they just picked some companies for it.
They did. Just this past week, they announced the selection of 4 really crucial companies: OKLO, Terrestrial Energy, TriSo-X, and Valor Atomics. And significantly, these aren't just fuel companies, they're all developing different advanced reactor designs themselves.
Ah, so it's not just generic funding. It's tying the fuel supply directly to the specific reactor types being developed here.
Precisely. They need to make sure the fuel being produced matches the fuel specs for the reactors that are actually going to be built. The goal here is incredibly ambitious. This program is meant to support the fuel needs for, I think the number is 11 different advanced reactor projects.
11 projects.
All currently planned for deployment by the late 2020s, without a stable, reliable Western source of HALEU. All those innovative designs, including potentially the Natrium we just talked about, and those NuScale SMRs for TVA. They're basically non-starters.
So this DOE program isn't just helpful, it's fundamental.
It's arguably the most essential foundational step needed right now to really accelerate SMR commercialization and move away from that reliance on Russia.
Okay, so government action is crucial. But we're also seeing industry players teaming up, right? Collaborating across borders to share the load. Like this partnership between OKLO in the US and Blykala in Sweden.
Yes, that's a perfect example of smart industrial strategy playing out.
Yeah.
OKLO developing their Aurora-fast microreactor, and Blykala working on their sealer lead-cooled system. They signed a joint technology development agreement.
And what exactly are they sharing? Is it designs or something else?
It's focused on the really hard, expensive stuff. They're pooling resources on materials research, finding metals and ceramics that can handle extreme conditions. They're looking at component sharing, maybe using the same qualified suppliers. They're coordinating on supply chain sourcing, which is a nightmare for everyone right now, and navigating licensing hurdles.
So basically tackling the shared headaches of building these advanced machines.
Exactly. Advanced reactors don't use off-the-shelf parts from the hardware store. They need highly specialized materials that can withstand intense heat, radiation, corrosive coolants.
Things like molten salt or liquid lead.
Right. So by collaborating, they leverage OKLO's connections to U.S. vendors with Blykala's expertise in the European market and their specific lead cooling knowledge. OKLO's leadership said publicly this joint effort will significantly de-risk the deployment of advanced reactors.
Makes sense. It's just more efficient, faster than each trying to reinvent the wheel alone.
Especially when facing the same supply chain bottlenecks, it's about compressing those deployment timelines.
Before we move on from fission, I think it's worth pausing for a second. We saw the retirement of a long-serving reactor in Belgium this week, T-Hunge 1. It feels like a moment to reflect on what these machines actually achieve over their lifetime.
It really is a profound historical marker. T-Hunge 1 disconnected after 50 years, 5 decades of continuous operation, most
50 years. And the output.
Over its lifespan, that single plant generated over 327 terawatt-hours of carbon-free electricity.
Which is an astronomical amount of power.
It's immense. And the research team's analysis estimates that avoided somewhere around 148 million tons of co-Euro emissions. It just underscores the huge, proven, long-term climate benefit that high-density energy sources like nuclear have already delivered.
So as we're looking forward to this next generation of advanced reactors,
we should remember the goal isn't just any clean energy. It's securing massive amounts of reliable, proven clean power. And that's the legacy T-Hunge 1 represents, even as its decommissioning begins.
A really important context for all the new stuff we're seeing. Okay, quick pause here. We really love hearing your thoughts on all this. If you're watching on YouTube or listening on your favorite podcast app, definitely drop a comment. Let us know what you think about these energy breakthroughs. Are SMRs really the silver bullet for AI's power needs? Or are there maybe regulatory hurdles or public acceptance issues we haven't even fully seen yet? We want to know what you think. All right, let's shift gears now. From advanced fission to, well, the ultimate energy dream for many, fusion. For decades, fusion felt like it was perpetually 30 years away, right? That was the old joke.
It was always the joke, yeah. But the work reported this week, gathered by our research team, it really confirms that fusion is moving very aggressively now from just lab science to immense real-world engineering challenges.
It's becoming less about proving the physics, more about building the machine.
That's exactly the transition we're seeing. It's about solving incredibly complex engineering problems at an industrial scale. And at the big international ITER project down in France, we saw 2 really critical hardware milestones hit this week. Things getting installed, getting finished.
Okay, what were these huge pieces of kit? And why do they matter for ITER's timeline?
First, they completed the installation of the first gyrotron. Now, think of a gyrotron as like a massive, hyper-advanced microwave oven on steroids.
Okay.
You need these things because they generate incredibly powerful millimeter wave beams. And those beams are what's needed to heat the plasma electrons up to the mind-boggling 150 million degrees Celsius.
150 million degrees. Just incredible heat.
Required for the fusion reaction to actually happen efficiently.
Yeah.
And just manufacturing and installing a device that can reliably generate and control that kind of energy, it's a monumental engineering feat in itself.
Okay, that's one piece. What was the second? Something about the central solenoid. Sounds important.
It is. It's literally the backbone of the whole tokamak machine. The final module for the central solenoid magnet, it was completed and shipped by General Atomics over in the US. This thing is the largest pulsed superconducting magnet ever built by humankind.
The largest ever.
Its job. Its function is absolutely crucial. It induces a powerful electrical current within the plasma inside the donut-shaped tokamak. That current is what helps heat the plasma initially and, more importantly, confine it, keep it stable, and sustain the fusion reaction.
So the gyrotron gets it hot, the solenoid squeezes it and keeps it going.
That's a good way to think about it. And the fact that these massive, complex components built by different partners in different countries, ITER, involves 35 nations are now arriving, getting installed. It signals a very deep, sustained commitment. It shows the engineering is becoming real.
It's moving from physics diagrams to actual physical hardware being bolted together.
The physics check is sort of done. Now it's the supply chain and engineering integration check.
And it's not just ITER. The private sector's pushing hard too, especially in a different approach. Inertial fusion energy, IAE, using lasers.
That's right. And here we saw news from Blue Laser Fusion, or BLF. They received a U.S. Department of Energy Infuse grant. Infuse stands for Innovation Network for Fusion Energy.
Okay, an infuser grant. What's the focus of their project?
The collaboration is specifically about developing advanced optical interference coatings. These are ultra-thin, multi-layered coatings for the mirrors and lenses used in BLF's high-pulse energy lasers.
Coatings. That sounds kind of small detail. Why does that merit part of a, $6 million DOE investment round?
But it's absolutely vital for IFE. See, BLF's concept, like other laser fusion ideas, needs incredibly powerful lasers to zap a tiny fuel pellet, compressing and heating it extremely rapidly to trigger fusion.
Okay.
Now, if you want a power plant, not just a single experiment, your lasers can't just fire once and then cool down for hours. They need to fire many times per second, continuously.
Right, for steady power output.
Exactly. And the mirrors and optics inside that laser system have to withstand that relentless barrage of high-energy pulses without degrading, or, worse, failing. Even a tiny flaw in a coating under that stress can cause the laser to basically burn right through the optic,
Shutting the whole thing down.
shutting down the reactor. So this grant is about accelerating the research into making these coatings super durable, highly reflective, able to handle the heat and power load reliably, pulse after pulse after pulse. It's a key step in moving IFE from, single-shot proof of concepts towards an actual industrial power plant design.
So technical progress is happening, both big public projects and private innovation. But that needs policy support too. And we saw major policy action in Europe, specifically Germany, making a big strategic bet on fusion.
We did. Germany's federal cabinet approved a national action plan called Germany on the Path to a Fusion Power Plant. And they're backing it with serious money. Over $2 billion in funding just by 2029.
2 billion euros. That's a significant commitment.
Yeah.
But is it just funding or is there more to it?
The funding is important, obviously. But the real news here, the thing that gets investors excited, is the policy mechanism behind it.
Which is?
Regulatory certainty. The plan's most critical part is its focus on creating clear, streamlined regulatory pathways specifically for fusion.
Separating it from the old fission rules.
Exactly. Right now, fusion projects often get tangled up in decades-old nuclear fission laws, which frankly makes very little sense. Fusion power plants have fundamentally different safety characteristics, no risk of meltdown, no long-lived high-level radioactive waste like fission produces.
So applying fission rules is just inappropriate and slows things down.
It's inappropriate, burdensome, and creates huge uncertainty for developers and investors. By creating a specific, fit-for-purpose regulatory framework now before commercial plants are even built, Germany's sending a powerful signal.
What's the signal?
The signal to private fusion companies and their investors is, if you develop your technology here, The path from your pilot plant to a commercial power station will be predictable. It won't get bogged down in outdated, irrelevant legislation. That certainty is absolutely essential to attract the billions more in private capital needed to actually commercialize fusion energy.
Okay, so the first section's really covered the big push for the hot core, the dense, reliable power. This next section, though, it feels like it shows the other side of the coin. Pulling back from other potential pathways, we saw a really stark high-dollar policy reset from the U.S. government this week.
We certainly did. A major shift in focus confirmed by the actions. The U.S. Department of Energy abruptly terminated 321 financial awards. These were supporting 223 different energy projects.
Terminated, just canceled.
Canceled, pulled the funding. And the total savings, according to the research team's analysis, is around $7.56 billion.
Wow, $7.5 billion. That's a massive course correction. That wasn't just trimming around the edges.
Not at all. This was a significant strategic reallocation, let's say.
And the research compiled by our team, it showed where those cuts were concentrated, didn't it? It wasn't across the board.
No, it was very targeted. The cuts landed heavily on two specific decarbonization pathways: regional clean hydrogen hubs and large-scale carbon capture and sequestration, or CCS, projects.
So projects trying to produce hydrogen cleanly or capture CO2 from industrial sites or power plants, those took the hit.
They took the brunt of it. We saw huge awards getting canceled, projects for CCS at cement plants, gas-fired power facilities, big grants for hydrogen production, hydrogen pipelines, hydrogen storage, terminated.
Okay, let's try to synthesize this. On one hand, you've got the government utilities like TVA committing billions to gigawatts of proven dispatchable nuclear, the hot core.
Right.
And on the other hand, they're canceling $7.5 billion tagged for these other, maybe less certain technologies like hydrogen and CCS. What does that tell us about the strategic thinking right now?
It sends a powerful, if maybe implicit, policy signal. The government seems to be deprioritizing technologies that face, well, significant economic uncertainty.
Like whether hydrogen can compete on cost or if CCS can scale affordably.
Exactly. Plus, those technologies face immense technical scaling challenges. And, maybe most importantly, they require extensive, entirely new infrastructure. Think about dedicated co-Euros pipelines stretching hundreds of miles, or a whole new network for transporting hydrogen.
Which is hugely expensive and faces massive, not in my backyard issues. Right.
Yeah.
Citing those pipelines.
Enormous capital costs, huge regulatory hurdles, significant public opposition potential. By contrast, they seem to be leaning into dispatchable, grid-ready nuclear power, which often can plug into existing transmission lines, maybe on former coal plant sites, and deliver reliable power directly to those high-demand industrial centers relatively quickly.
So the hot core is winning out partly because it seems like a more direct, maybe more certain path to get the power where it's needed reliably.
It looks that way. It appears to offer a more pragmatic route towards grid stability and supporting that industrial growth compared to the massive infrastructure build-out required for some other pathways.
Okay, shifting from that U.S. internal pivot to the global stage, we saw a major geopolitical realignment, and it involves uranium, the very feedstock for this hot core energy, the deal between Niger and Russia's Rosatom.
Yes, this is a really complex story with multiple layers. Niger, which for decades has been a major supplier of uranium, especially to France.
Right. France relies heavily on Nigerian uranium for its nuclear fleet.
Historically, yes, but now Niger's new leadership announced plans to build two large 2 GOW nuclear reactors. That's 4 gigawatts total capacity. And they're doing it with Russia's state nuclear corporation, Rosatom.
Wow. So switching from being a uranium supplier to France to getting nuclear power plants built by Russia, why is that such a big geopolitical deal beyond just the power contract itself?
Well, it solidifies a major post-colonial pivot that's been underway. For decades, you had a situation where the wealth generated from mining Niger's vast uranium reserves. Well, it primarily benefited France and European utilities. Meanwhile, Niger itself remained one of the poorest countries, incredibly energy poor.
Right, the irony of exporting energy fuel while having little electricity domestically.
Exactly. The new military government there is very aggressively realigning its foreign policy, moving away from France, its former colonial power, and towards partners like Russia. And Russia often comes to the table with these comprehensive infrastructure deals. They offer financing, construction, fuel services, training, the whole package.
So this deal effectively displaces French influence in a sector that was really vital to France.
It certainly seems to be a major step in that direction. It impacts France's energy security and its historical sphere of influence in the Sahel region.
And for Niger itself, what's the motivation? It's explicitly about development.
Absolutely. It's framed entirely around domestic development and sovereignty. Currently, only about 20%, 1 in 5 people in Niger has access to electricity.
Just 20%.
So they're essentially saying, we're done just being a raw material exporter for others' benefit. We have uranium, we're going to use it to build energy sovereignty. They want to power their own industrialization, improve lives, provide that 4 gigawatts of stable power to their own citizens. It's a strategic move with huge implications for the global uranium market, nuclear geopolitics, and the balance of power in West Africa.
When we talk sustainability, the focus is almost always carbon, CO2. But the data our research team pulled together, it shows that high-density energy, like nuclear, is starting to win arguments on other really crucial sustainability metrics, especially land use.
Yes, the land use equation. It's rapidly becoming maybe the limiting factor for deploying low-density renewables like wind and solar at the massive scale needed for deep decarbonization.
And we saw a perfect example of this conflict playing out this week.
We did a case study with the Horse Heaven Hills wind farm project in Washington state. This was already a huge proposed project. It faced such intense local opposition that the state siting council ended up recommending approval, yes, but with restrictions so severe
That the project is basically crippled.
the projected generating capacity will be effectively cut in half. It makes the economics questionable and highlights the difficulty.
And tell us more about why people were opposing it. It wasn't the cost of the wind turbines, was it?
No, not at all about the project economics from the developer side. The opposition was entirely centered on non-technical factors, social and environmental impacts.
Like what specifically?
Concerns included the severe visual impact, hundreds of massive turbines dominating a valued landscape. Noise pollution was another factor. There were deep cultural resource concerns from local Native American tribes who have historical and spiritual connections to that specific land.
Okay. And wildlife impacts too.
Critically, yes.
Huh.
Threats to endangered wildlife, particularly the ferruginous hawk. Concerns about habitat destruction and the risk posed by the large rotating blades.
So this is the real-world trade-off, isn't it? With a sprawling, low-density system like large wind farms, you might solve the carbon problem locally, but you create these immediate, intense conflicts over land, culture, and wildlife.
Exactly. When your project requires thousands upon thousands of acres and hundreds of structures that are hundreds of feet tall, the chances of running into conflicts, protected species, sacred sites, or just upsetting the local community visually, they skyrocket.
And how does that contrast with, say, an SMR?
Well, you contrast that sprawling, often contentious footprint with the small, predictable footprint of an SMR, which can often be sited on existing industrial land, maybe a brownfield site, or reusing land from a decommissioned coal plant. The permitting process, the social risk, the environmental impact area, it's just vastly smaller and potentially more manageable.
So utility planners, when they're looking ahead 10, 20 years, they have to factor in this growing land use constraint.
They absolutely do. They're hitting a ceiling in some places on how much low-density renewable capacity they can realistically site and build without sparking major opposition. And that reality reinforces the need for density. It pushes them towards that hot core imperative.
Okay, so land use is one angle. What about cleaning up the supply chains for clean energy? The minerals needed, rare earths, for instance, their extraction and processing can be pretty dirty.
That's a major challenge. The hypocrisy, some would say, of clean tech relying on polluting supply chains. But we saw a potential breakthrough there, too, this week.
Yeah.
An advance in recycling rare earth elements, REEs, using a technique called flash joule heating, or FJH. This came out of a partnership between a company called Metallium and researchers at Rice University.
Rare earths. Those are crucial for magnets and EVs and wind turbines, right?
Exactly. High-performance permanent magnets rely heavily on elements like neodymium and dysprosium, and conventionally getting these elements, whether from virgin ore or from recycling old magnets, involves hydrometallurgy.
That sounds like
It involves using large amounts of water and really harsh hazardous acids to dissolve the metals out. It's energy intensive, produces significant toxic waste sludge. It's a major environmental headache, often concentrated in just a few places globally.
Okay, so how does this flash joule heating, FJH, change that game?
FJH is completely different. Instead of dissolving things slowly in acid, it uses rapid, intense pulses of high amperage electricity.
Yep.
This instantly heats the material, say, crushed up old magnets to extremely high temperatures, like 3,000 degrees Celsius, in milliseconds.
Flashing it with heat.
Exactly.
Mm.
And this intense thermal shock can directly separate the valuable rare earth elements from the other materials, often vaporizing impurities or converting components into easily separable forms, bypassing the need for acids entirely in many cases.
And the benefits are?
Huge. The research our team looked at indicates this process achieves up to an 87% reduction in energy consumption compared to traditional methods. And critically, it completely eliminates the use of water and those harsh acids.
Wow. No water, no acid, much less energy.
It makes RE recycling much cleaner, potentially faster, and because the equipment might be more compact, it could allow for more decentralized processing, maybe closer to where the old EVs or wind turbines are actually being dismantled.
So it tackles a major environmental bottleneck and maybe even a strategic vulnerability in the clean energy supply chain.
Precisely. It could help create a cleaner, more distributed, maybe more resilient circular economy for these absolutely critical materials.
Okay, one last piece of corroborating evidence. This comes from Japan, looking at the real-world grid impacts of bringing nuclear power back online. What did the data show there?
Yeah, this is a really vital data point about grid integration realities. Japan has been gradually restarting its nuclear reactors after the Fukushima shutdowns. They now have 14 reactors back online.
And that's successfully providing more low-carbon baseload power, presumably.
It absolutely is boosting their clean energy supply. However, the data compiled by our research team indicates an interesting side effect. It's led to a noticeable increase in the curtailment of wind and solar generation.
Curtailment meaning they're telling wind and solar farms to shut down, even when they could be producing power.
Exactly, turning them off. The curtailment levels reached up to 2.3% of the potential wind and solar output in some regions. Now, this isn't because the renewables failed. It's often due to grid constraints and the inflexibility of the other power sources.
So the steady, inflexible nuclear baseload is kind of crowding out the variable renewables when the grid gets congested.
That's what can happen on a constrained grid. When you have a large amount of inflexible, must-run baseload power like traditional nuclear, running flat out, it fills up the available grid capacity. Then, if it's sunny and windy and demand isn't super high, there's simply no room left on the wires for all the renewable power being generated, so it gets curtailed.
So this proves that just adding density isn't enough. The type of density matters.
It highlights that density is necessary, yes, but that firm, flexible capability we talked about with Natrium's storage, that becomes really vital. You need your dense power sources to be able to adjust their output to make room for renewables when they're abundant. Otherwise, you risk having your new clean nuclear generation inadvertently undermining the economics of your other clean energy investments, like wind and solar. It's a crucial lesson for grid planning everywhere. Hashtag outro. So as we wrap up this deep dive on Tomorrow Unveiled, looking back at all the data from the past week or so, there are really three crucial insights that stand out. Themes corroborated across the commercial deals, the policy shifts, the tech advances. First, this energy transition, particularly for the grid, it's now fundamentally market-driven. That commercial validation, the huge 6 GWTVA deal, it's now actually running ahead of the technical demonstration in some ways. Why? Because the demand from AI, from data centers, is immediate, it's confirmed, and it's non-negotiable. The market risk, as we said, has flipped.
Right. The risk of not having the power is the driving force.
Exactly. Second, there's this intense, almost singular focus now on the supply chain. Governments are treating bottlenecks, especially HALEU fuel, not just as technical hurdles, but as core national security priorities. They recognize HALEU is the immediate choke point, the limiting factor for getting advanced fission deployed at scale. Everything else depends on solving that.
The fuel is foundational.
It is. And third, the density imperative is becoming undeniable. Those land use conflicts, like we saw in Washington state, combined with the hard realities of grid constraints and the absolute need for reliable power. It's forcing a pragmatic shift, a move towards high-density solutions like nuclear, because they offer a more realistic path to scalable decarbonization that actually respects the physical and social limits we face.
Absolutely. But, as always, the path forward isn't guaranteed, is it? There are still huge challenges.
Oh, absolutely. Scaling that HALEU supply chain globally, quickly, that's an immense task. Navigating the really complex geopolitical shifts like the situation with Niger, Russia, and France, that impacts fuel supply and global stability.
And ensuring our regulations can keep up, right? modernizing rules for Gen 3 fission and for fusion, like Germany's trying to do, without accidentally stifling the very innovation we need. That's a tightrope walk.
A very difficult balancing act.
So, the provocative final thought we want to leave you with today is this. Are we just seeing a promising narrative emerge with green code, hot core? Or are these simultaneous breakthroughs, commercial, policy, technical, are they genuinely enough, happening fast enough, to actually outpace the incredible non-negotiable energy demands of our digital future by the time we hit the 2030s? The race is definitely on. If you found this discussion insightful, and we hope you did, please take just a moment to like this video if you're on YouTube. Subscribe to Tomorrow Unveiled, maybe even hit that new hype button apparently that helps us reach more viewers. And definitely turn on notifications so you don't miss our future updates. And if you're listening on an audio platform like Apple Podcasts or Spotify, we would be incredibly grateful if you could leave